2.2, quiz questions, part 2. Questions from number 4 through number 6. Question number 4. Which of the following measures is better for algorithm efficiency? Here we are talking about algorithm efficiency measurement. That concept, that issue. Okay. So in the lecture, I explain, in order to get a good measure, we want something that is stable. So this is important property. We need stability property. We need that. So what do you mean stable? Stability here. Because we don't want the measure relies on hardware, right? Hardware, the machine. Yeah. Some people use super fast computers, but other people use relatively slow computers. That may not be fair comparison, right? So we want to avoid that. So we want some measure that does not rely on your hardware. Yeah. Also, another possibility, the factor, the third one, the biggest one, hardware factor. The second, the program implementation. The program implementation, even given the algorithm, but different programmers, they may implement the same algorithm differently, right? Yeah. So programmer with different implementation yeah. Right? Yeah. Good programmers, they can write super efficient, so they do not have any redundant code. Okay? The memory usage, so all things make perfect. But there are some bad programmers, so they do not know how to use the resources efficiently. So they may waste a lot of resources. Sometimes the memory leak, messed up. Yeah. Barely get the correct output. Some programmers like that. Do you want to make your algorithm efficiency measurement rely on that kind of program implementation difference? Right? Yeah. You don't want to. Yeah. So for that reason, we need a stable measurement. So the number of basic operations, we do counting. We count the number of basic operations. That measure, it does not rely on the hardware. It does not rely on the program implementation. So that is stable, right? So that kind of background, you need to have that. Okay? Yeah. Question number 4. Question number 5. When we evaluate a polynomial, is it possible for us to apply the factorization technique to reduce the number of multiplications? Here, I'm asking you details in the algorithm. So here, because I want to check if you really study the videos, the lectures. Here, the details. Evaluate polynomial. Think about how did we get the Horner's rule? that procedure, that analysis procedure, how did we get that? We did factorization. That's the key property. We use the factorization property in our development. So recall that. That's the key property. Okay? Yeah. So is it possible to apply factorization technique, reduce the number of multiplications, right? That's the essence. That's the essence of Horner's rule, right? So this is exactly, so that's the essence of Horner's rule. Okay? Yeah. Yes. So you need to have that background. You cannot just make guess. You cannot just make guess. If you answer these questions by making guessing, you cannot get very high grades. You cannot. Okay? Yeah. Especially, you can think about, you can look at some of the questions. I tried to trick you. So I tried to, create use some special sentences, try to mislead you to a wrong direction. Yeah. So many times I do in that way, mislead you, try to trick you a little bit, because if you can find the problem, if you can avoid that kind of, noise, I can call that noise, okay? If you can avoid that kind of noise, then that proves your understanding is pretty solid, okay? Yeah. All right. The last question of part 2, question number 6. Given any polynomial, if we use the Horner's rule to evaluate, we always get the minimum number of multiplications. This one requires deep understanding, a little deep understanding. Okay, why? The reason is very simple. Because based on our impression, after we learn Horner's rule, our impression is Horner's rule is very efficient. That's our impression, right? Horner's rule is very efficient. That's correct, right? Nothing wrong here. All right, so now you have this impression, very efficient. Then you tend to make the conclusion that no other way can beat Horner's rule. You tend to have, okay? So I just say you tend to have that kind of impression. Nothing can beat Horner's rule, even under the special situation. Okay? Under special situation. But I give you example. I give you counter example. That is wrong. So remember, I give you a counter example. So let me tell you my counter example. 1 plus x to the 4th, okay? We expand it, all right? 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth Pascal triangle, right? I told you, the coefficients you have here, we use that famous Pascal triangle. Okay? Yeah. So I assume you know that. Okay? All right. All right. So here, suppose I give you this polynomial. I ask you, you apply the Horner's rule to calculate this polynomial, and based on our result, you need 4 multiplications, right? Yeah, the same number there, 4 multiplication. All right? Yeah. All right. But we know for the special case, this is a special one, not the general one. All right? Because this polynomial can be written as 1 plus x to the fourth. All right? Now we know 1 plus x times 1 plus x. So that's 1 multiplication, right? The first multiplication. Okay? The second multiplication, 1 plus x squared, because we already have the value from the first multiplication, right? You just multiply itself, you have the second multiplication, 2 multiplications, right? That means for this one, we only need 2 multiplications. Okay? Better than Horner's rule, right? From 2 to 4. Okay? The reason we take advantage of the special structure, right? Here we use the repeated squaring. So this counter example, we use the repeated squaring technique. How about that? Okay, so here you can see we need this much background to answer this question correctly. All right, yeah. So we can always get the minimum. That's false because we have this counter example telling us that's not the minimum number of multiplications. All right, okay. So that's the part 2. All right, so next we have part 3 to complete all the 10 quiz questions.